Let's first illustrate the problem of overfitting using a very basic curve fitting example. So in this case, we have a data set of 20 data points that clearly shows some kind of nonlinear relationship. And now the task is to find a polynomial of a degree p that best fits these data points. And on the left-hand side, if we choose a polynomial of degree 1, which means on our polynomial it's just a line, that we can clearly see that this line is not capable to follow this nonlinear trend. In this case, we talk about underfitting. Simply speaking, our model is not powerful enough. Our degree p is too low. If we set a polynomial of degree 2, then we get a much better fit, because now our fitted line quite captures the overall trend in our dataset quite well. And we could expect that this model would behave quite nicely on unseen data points. But of course, if we keep increasing the degree, for example in this case p equals 8, then obviously our model becomes too powerful in a sense that it's now more capable to really try to fit each data point as closely as possible. And since in practice data points also always contain some form of noise, we learn too much. So overfitting can be thought of as learning too much. So here we can see, particularly for example on the right-hand side, that our model, by trying to fit the last data point as good as possible, makes some very, very weird decisions. So for example, if we would have a new data point, for example here, then we would make a very bad prediction. So this model would fit badly on unseen data. So how does this problem of overfitting map to our initial example of predicting the sentiment of a movie review? So let's assume we don't have that many reviews. And let's also assume that in these low number of reviews, we have some kind of artifact or some kind of noise. In a sense that all positive reviews contain many pronouns and almost no negative reviews contain pronouns. So what this now means is that if we would have this data set and we would train a logistic regression fire, then our classifier would overemphasize the importance of pronouns. Because the classifier can only use the information that we give this classifier. In this case, we give them information that contains some kind of artifact, some kind of noise, so the classifier will learn from this noise. Which means that most likely we will see a very large value for theta 4, because theta 4, of course, corresponds to feature 4, which is the number of pronouns. Which then means that any time we have a new unseen negative review, which in this case might contain many pronouns, it will most likely be misclassified. Because every time the classifier sees many pronouns, the classifier would always think, okay, this must be a positive review, because we overemphasize this feature. So what we can do about this, and the basic approach to handle this is what is called regularization. And regularization basically is based on the observation that we talk about a model is too powerful if we see very large theta values. And regularization is essentially the process of penalize large theta values. And how can we do this? We can do this by extending the loss function. So we say, okay, the loss function not only captures how good our predictions are, but also how large our theta values are. In other terms, the larger these theta values, the larger our loss function should be. So if we minimize our loss function, we also kind of implicitly guarantee that the theta values won't become large. And here is basically regularization applied for the cross entropy loss. So if you recall, this was our basic cross entropy loss that we've seen before. And the only extension we do here is to add another term. And here we show two examples called L2 regularization and L1 regularization that have different pros and cons, but we skip these details. But essentially both of these regularization terms sum up all the theta values, which means if the theta values are large, this term will be large, and if this term is large, then the loss will be large. So if we minimize the loss function, we try to kind of keep these theta values as low as possible. And lastly, this lambda value is just some kind of regularization parameter that tells us how strong or how much impact this regularization term should have. And of course, since we changed the definition of our loss function by adding this term, also the gradient changes. But the good thing is, this is not a big deal, because this change in our loss function is just an added term. And we know that the gradient of a sum of two terms is just the sum of the individual gradients. So we can calculate the gradients individually. And in case of, for example, L2 regularization, this is just the gradient for the L2 regularization. So this is the only change we need to do. Basically, the calculation of the gradient also changes. But the good thing is there's no changes in the gradient descent algorithm itself. It's simply that the calculation of the gradient is different, but anything else with respect to gradient descent remains exactly the same.